Hello guys, welcome back to the Analog channel, and today we will be talking about buck converter. The idea is to have an DC input voltage like 12 volts and a circuit capable to reduce this input voltage to a lower output voltage and constant output voltage like 5 volts, okay? And this is the circuit that was used to implement our buck converter utilizing the 555 IC like a PWM. Here we have our 555 IC and other ICs like LM358 and TL431. So let's get started. So how to reduce the amount of voltage in a load? We have two methods. The first one is the linear regulator, where we have here a voltage divider. Part of this the voltage source will stay across R2 like this, VA, and the other part will stay across the R load. VB, where VB is V1 times R1 over R1 plus R2, okay? And what is the problem with this converter? The problem is that the current load is passing through R2, and this means that we will have a lot of losses in R2, okay? So this converter is not efficient. Let's say we have 5 volts at the load and 10 volts at the source. We can calculate our efficiency like this: V out over V in, that is equal 5 over 10 or 50%. So we are 50% efficient in trying to convert 10 volts in 5 volts using the linear regulator. It's not a good efficiency, okay? So let's see the other method to convert the voltage. Instead of use a linear regulator, we can use a switched regulator like this one. Here we have a key, electronic key, that will receive the pulses to switch on and off, and here we have our load, our load, okay? Since we have electronic key, when we put a positive pulse at the key, an on pulse, the switch will close and the voltage will pass through the key until to the load, okay? So we apply 10 volts at the load. So if you cut off the voltage at the key, switch off, we will apply 0 voltage at the load and repeat the process. Apply the voltage, switch on, and cut the voltage, switch off. If you pay attention, our load are receiving 10 volts and 0, 10 volts and 0. This means that we have an average voltage at the load that can be calculated like this: T on over T times V in. Okay, here we have T on, T off, and the total time is at T or period, where our duty cycle is T on over T. Okay, so the process of switching a voltage at the load will give us an average voltage, and this average voltage is the total voltage at the load. What is important here? The important is that when the switch is on, this switch is zero because we don't have voltage added at the switch when it's on. So the power, total power, is zero, and we don't dissipate energy at the switch. And when the switch is off, the total voltage at the switch is VCC, but we don't have current at the switch, and the total power dissipated is zero, so we don't dissipate energy at the switch. This is why the buck converter is most efficient than the linear regulator. But in practice, this is not totally real, because we spent some energy at the switch, but the efficiency is much better than the voltage converter using linear regulator. Okay, so if we have a duty cycle of 10%, our output voltage will be VO, it's equal 0.1 times 10 volts. It means we have 1 volt at the output. If our duty cycle is 50%, we will have 0.5 times 10. It means that we have 5 volts at the output. And if we have in duty cycle a duty cycle of 90%, we will have 9 volts at the output. Okay, here we have an average of 1 volt at the load. At the second case, we have a duty cycle of 50% and the output voltage of 5 volts. And at the last case, we have a duty cycle of 90% and output voltage of 9 volts. Okay, so here's our buck converter schematic. We have a MOSFET here. This is our key. We have an LC filter. To eliminate the switched frequencies and let to pass to the load only the average voltage. And we have a free diode here to eliminate or dissipate the energy stored in our inductor. Okay, so we will be switching our key, and the LC filter will let to pass only the average component to the load. Okay, this is why we use this LC filter. Well, let's see the waveforms. Okay, at the first case we have a switched on period. The key is switched on, and we have this yellow color here, meaning that the switch is on. When the switch is on, the voltage Vi is 12 volts because our key is closed, and this 12 volts pass through the key until the beginning of our inductor. So we have 12 volts at the beginning of our inductor. The other side we have 5 volts, the output voltage VO, and the voltage at the inductor is Vi minus VO. 12 minus 5, it's equal 7 volts. Okay, so we have plus minus 7 volts applied to our inductor, and the current is in this direction. At the second interval we have the switched off period and the key is open. Okay, so when the key is opened, we know that the inductor will try to maintain the current through his terminals, and to do this he will invert the voltage at his terminals. So we will have minus and plus volts in the inductor, and the inductor will discharge through the load and the diode. Okay, and we will dissipate the energy stored. Alright, this is our buck converter. So here we have our buck converter circuit. First we will start looking at our 555. Our 555 is working as a PWM circuit. We don't need this, neither this, and here we can do this. Okay, this I will call RA, and this is our RB, and this is our C. The 555 is working at a frequency, switching frequency, that can be calculated by this formula. Okay, the 555 is not working at a fixed frequency because the frequency will depend on the voltage at the pin 5, and this voltage is not constant. The PWM will be generating at the pin 3 the output pulses. These output pulses will be switching on and off our key, our MOSFET key. Here, our MOSFET key will work in conjunction of our buck converter. Here is our buck converter, and this is our LC filter. Okay, here are our load. The idea here is to get the output voltage and to compare it with a fixed voltage reference. If the fixed voltage reference is greater than the output voltage, we will inform the 555 that he needs to increase the switching frequency to arise the output voltage. Okay, if the output voltage is lower than the fixed reference, we will inform the 555 that it don't need to switch the key. Okay, he needs to cut off the key. Since our load is not connected at the common point of the source, we need to use a differential amplifier to get the output voltage. So when we have the output voltage here, the out, we will sample this output voltage to compare with a fixed reference In this case we are using the TL431 to generate 2.5 volts as a fixed reference. So when we have 5 volts at the output, the sample will supply 2.5 volts to the LM358. The LM358 is being using like a error amplifier, and will put at the output the difference between these two input voltages. Here we have our error signal. Okay, this is enough for today. In the next video I will show you the implemented buck converter, and we will discuss the results. Thanks, see you.